We live in a transformative era for astronomy, often referred to as the age of shifting paradigms. Thanks to next-generation technologies, astronomers are dismantling long-held beliefs about the cosmos. Ideas that once seemed rock-solid, like how stars and planets form, are now being re-examined under the lens of cutting-edge telescopes, instruments, and data analysis powered by artificial intelligence. Among these revolutionary changes, one recent discovery stands out. It challenges a central tenet of planetary science: the nebular hypothesis. This widely accepted theory proposes that stars and their planets form together from clouds of gas and dust called nebulae. When gravitational collapse occurs, a new star ignites at the center of the cloud, and the surrounding material flattens into a disk. Over time, this protoplanetary disk gives birth to planets, moons, and other celestial bodies. Under this model, scientists have long assumed that the materials composing a planet should closely match the gases and dust in the protoplanetary disk from which it formed. However, observations of a young exoplanet known as PDS-70b have turned this assumption on its head. A research team has discovered a puzzling mismatch between the atmospheric composition of this planet and the materials in its natal disk. This finding suggests that planetary formation may be far more complex than previously thought. The study was led by Dr. Chichun Dino Xu, a postdoctoral researcher at Northwestern University's Center for Interdisciplinary Exploration and Research in Astrophysics, see ERA. Collaborating with scientists from Caltech, UC San Diego, and UCLA, Xu and his team focused on PDS-70b, a still-forming gas giant located 366 light-years from Earth in the constellation Centaurus. This young planet, roughly 5 million years old, orbits a variable star of the same name. What makes PDS-70b truly remarkable is its location. It resides within the inner cavity of its star's protoplanetary disk, a region rich in gas and dust where planets are actively forming. Jason Wang, an assistant professor of physics and astronomy at Northwestern and a key advisor on the study, explained the significance of this system. This is one of the only known systems where we can directly observe planets in the process of forming alongside the materials from which they are built. It's like having a snapshot of the construction site where worlds are made. To study PDS-70b, the researchers used the Keck Planet Imager and Characterizer at the Keck Observatory in Hawaii. This state-of-the-art instrument allowed them to isolate and analyze the faint light emitted by the planet, despite the overwhelming brightness of its host star. By capturing the planet's spectra, its unique light fingerprint, the team detected the presence of carbon monoxide and water in PDS-70b's atmosphere. They then calculated the ratio of carbon to oxygen in the planet's atmosphere and compared it to the ratios observed in the surrounding protoplanetary disk. "We expected the ratios to align," explained Xu. Instead, the carbon in the planet was significantly lower than in the disk. This suggests our understanding of planet formation is overly simplistic. This discovery directly challenges the long-standing assumption that a planet's atmospheric composition mirrors the gas in its natal disk. The mismatch has profound implications for our understanding of how planets form and evolve. To explain this discrepancy, the researchers proposed two possible scenarios. The first suggests that PDS-70b might have formed early in the disk's evolution before the surrounding gas became enriched with carbon. The second hypothesis posits that the planet could have grown primarily by accumulating solid materials, such as ice and dust, rather than just absorbing gases. These solid particles would have released carbon and oxygen into the atmosphere as they evaporated, altering the planet's carbon-to-oxygen ratio. "It's not just about gas versus gas," said Wang. "Solids like ice and dust could be playing a major role in shaping planetary atmospheres. This means we need to expand our models to account for the contribution of solid materials. Until recently, studying the atmospheres of still-forming planets was virtually impossible. By the time most exoplanets become observable, their protoplanetary disks have dissipated, and the planets themselves have finished forming. However, advances in photonics technology, co-developed by Wang for the Keck telescopes, have made it possible to isolate the light from young planets like PDS-70b. These new tools allow us to take incredibly detailed spectra of faint objects located right next to very bright stars, Wang explained. It's like trying to spot a firefly next to a floodlight, and now we have the technology to do it. These capabilities enabled the team to capture unprecedented details about the PDS-70 system, setting the stage for future discoveries in planet formation. The researchers now plan to turn their attention to PDS-70c, a second planet within this extraordinary system. PDS-70c, like its sibling PDS-70b, remains in the midst of its formative stages, presenting another rare and invaluable chance to observe the intricacies of planetary evolution as they unfold. This system offers a glimpse into processes that are typically hidden from view once planets have fully formed and their protoplanetary disks have dissipated. By comparing PDS-70b and 70c, we can gain deeper insights into the formation history of this system, Xu said. Each of these planets may hold a piece of the puzzle, and together they can provide a more complete picture of how planets and planetary systems come into being. However, to fully grasp the mechanisms at play, we must expand our research to include other systems that exhibit similar characteristics. This discovery underscores the critical role of direct observations in reshaping and refining our theoretical frameworks. Historically, much of what scientists understood about planet formation came from indirect observations or models based on older data. The ability to directly observe young planets in their natal environments represents a monumental shift, enabling astronomers to test long-standing hypotheses against real-world evidence. As astronomers continue to explore the cosmos using increasingly advanced tools, they are poised to uncover more unexpected findings that challenge conventional wisdom. These efforts will likely force us to reconsider not just the mechanics of planet formation, but also the origins of the very building blocks of life itself. The insights gained from PDS-70c and systems like it may eventually lead to a deeper understanding of how diverse planetary environments evolve, and by extension, how they might support the emergence of life in the universe. The findings from PDS-70b serve as a compelling reminder of how vast and mysterious the universe remains. They underscore the intricate and diverse nature of planetary systems, revealing that the mechanisms governing planet formation are far more complex than we once believed. These discoveries push the boundaries of our understanding and carry profound implications for the ongoing search for habitable worlds and the possibility of extraterrestrial life. The realization that planetary building blocks can vary so significantly challenges long-standing assumptions about the conditions necessary for creating Earth-like worlds. If the components of planets are so diverse, it opens up new questions about the precise interplay between gas, ice, and dust in shaping planetary atmospheres. Could this complex interplay hold the key to understanding the origins of water, organic molecules, and potentially life itself on planets like Earth? These are the kinds of questions that drive scientific curiosity and inspire further exploration. As Xu and his team continue to delve into the mysteries of planetary formation, their work stands as a beacon for the future of astrophysics. In the age of shifting paradigms, such discoveries remind us that the essence of science lies not in definitive answers, but in the pursuit of ever deeper questions. The more we uncover about the cosmos, the more we recognize the boundless scope of what remains to be explored. Each breakthrough is not an end but a doorway to new realms of inquiry, fueling our desire to comprehend the universe and our place within its grand narrative.